Hi everyone, this is Aidan for Fluid Mechanics 101, and today I'm going to be talking about wall functions and how do they work. So just to give an overview of what I'm going to talk about, I'm going to talk about the background for what wall functions are, why they're needed in CFD codes. I'm then going to touch briefly on what are automatic wall functions and what is automatic wall treatment. And then we're going to dive in behind the scenes a little bit to look at what CFD codes actually do. And then to wrap up and finish up, we're just going to look at what values of Y+ should you be using in your CFD simulations to get the best results. So just to start with some background, if we look at profiles of velocity, temperature, or turbulence scalars in a fluid domain, we see a profile that approaches zero at the wall and has some quite steep gradients as we approach the wall. So if we look at the plot on the left, that's just a typical velocity profile that you might see, and the velocity is free stream far away from the wall, zero at the wall from the no slip condition, and as we approach the wall we see that the gradients get steeper and steeper as we approach the wall. And in a CFD code, a second order finite volume CFD code, the variation across the cells is linear. And as a result, if we want to capture those steep gradients close to the wall, then we have to use a large number of cells, and the cells get thinner and thinner as we approach the wall if we want to accurately resolve those gradients. So a typical mesh that you might see for a CFD solution is shown in the picture. This is just a 2D aerofoil plot, and we can see that in the direction normal to the wall, the cells get very, very thin as we approach the wall, and that resolution in the wall normal direction is much greater than the chordwise and spanwise direction. And what we see is that those cells in the wall normal direction are very thin, have a high aspect ratio, and if there's any skewness in those cells, then this can lead to poor cell quality. And this is bad for our CFD solver because poor cell quality can lead to instabilities and perhaps even divergence, and the large number of cells that are needed to resolve those gradients increase the solution time. So currently with the second order finite volume CFD, the way we resolve those gradients close to the wall is a piecewise linear approach, and we have to have lots and lots of thin cells to capture those gradients normal to the wall. But what if we could replace all of those thin cells with a single large cell instead? And the way we would do that is by, instead of having a linear variation between that cell centroid, the red dot, and the wall, we have a non-linear function instead. And that would allow us to use much larger cells, reduce the total cell count, and also improve the stability of our CFD solution. So that's really the motivation, but what is this nonlinear function and what would it look like? So the plot I've shown you there is actually the nonlinear function that we want to model. And this function is a plot of velocity, tangential velocity, and distance normal to the wall y. And this plot was generated from experimental measurements and direct numerical simulations of flow in a plane parallel channel, as you can see from the little sketch. And so in our CFD simulations, we really want to try and model that profile between the cell centroid and the wall, so then we can have our large cells and reduce the total cell count. So how do we do it? Now, wall functions are the empirical functions that we fit to that observed behavior close to the wall. And in the plot again, we've got tangential velocity plotted against wall normal distance, and the black solid line again shows that observed behavior close to the wall, and this is what we want the velocity profile to look like. And what we've got there are blue and green lines which show the empirical functions that we can fit to this observed behavior, and these are the wall functions. Now we can see that actually the profile is split into three regions, and this is the standard approach for modeling that observed behavior close to the wall. And for y+ values of less than 5, the left-hand region of the graph, we can see that that blue profile gives a very good fit to the observed data. And in the region on the right, for y plus values of greater than 30, we can see that that green line gives a very good agreement. And that green line is linear, and it should always be remembered with these plots, as they're typically shown, the x-axis is on a log scale, whereas the vertical axis, the y-axis, is shown on a linear scale. So actually that data fit, that empirical function in the log law region is actually a logarithmic profile, whereas in the viscous sublayer, in that section on the left, the variation close to the wall is actually linear. Now, in the buffer layer in between these two regions, we can see that the blue curve, the blue wall function, and the green curve, neither of them actually give a good agreement with the observed behaviour, and we're going to talk a little bit about those later and what we might do. So, what is the mathematical form of these functions, and how might we include them in the CFD code? So that blue line that we saw in the viscous sublayer is given by the function equation 1, y plus is equal to u plus. So the variation of velocity between the wall and the self-centroid is actually linear, remembering that the scale on those plots is logarithmic on the x-axis. And then that green line, so for y plus greater than 30, we've got a logarithmic variation of u plus with y plus. And those coefficients, kappa and e, are empirical coefficients that we use to fit the logarithmic profile to the observed data, and they're 0.4187 and 9.793 respectively. So we've got two fits to the data. We've got a fit for y plus less than 5, and we've also got a fit for y plus greater than 30. And at this point, it's worth stopping and actually just taking a minute to think about what y plus and u plus actually are and what they represent. So y plus and u plus are dimensionless units, often sometimes called wall units in the literature. You may see them called wall units. And y plus is the distance normal to the wall, and u plus is still the tangential velocity. But these are dimensionless quantities, and the reason we want to plot with dimensionless quantities is so that that behavior observed to the normal to the wall is universal, and it's valid for a range of flows with a range of geometries and flow speeds. And the quantity that we use to dimensionalize those properties is a velocity called the friction velocity, or u sub tau. And this is a reference velocity based on the wall shear stress, or the square root of the wall shear stress. And the reason we choose the square root of the wall shear stress to represent our reference velocity is because at the wall, the velocity at the wall is 0. So actually we need to choose a better reference velocity, because the free stream velocity far away is not really going to be effective here. So we use the square root of the wall shear stress to dimensionalize our coefficients. And it's important at this point to also point out that you could use another reference velocity, and some CFD codes use the square root of the turbulent kinetic energy, and we're not going to go into this in too much detail now, but it's something we could bring up later. So what about that buffer region in the middle between y plus of 5 and y plus of 30? Now, at the moment we saw that those blue and green curves don't actually give a good fit to that observed behavior in that region. So how are we going to model the buffer region? The most obvious approach we could use is notice that the blue curve and the green curve intersect at a y plus of 11.25. And so then the most straightforward approach would be to use a conditional if statement and say that u plus is equal to y plus if y plus is less than 11.25, or it's equal to the logarithmic variation if it's greater than 11.25. Now, this is the most straightforward approach to the buffer region, but it will give large errors because we've seen that both the blue curve and the green curve don't closely match that observed behavior in the buffer region. And it's this reason that CFD codes and CFD manuals often recommend not placing cells in the buffer region between a y plus of 5 and a y plus of 30, and this often leads to wall resolved meshes with y plus of less than 5 and wall function meshes with y plus greater than 30, because that behavior in the buffer region is really uncertain and hence can be quite inaccurate. So what's an alternative approach we could take? Well, an alternative would be to fit a single smooth continuous function through that entire range of data. And one example of a function we could use to use that is the Spalding wall function, which is given in equation 6. And this function is smooth, continuous and valid for the entire range of y+. So what does the Spalding wall function look like? Here you can see we've got the same plot as before with the observed data and the linear and log law wall functions, but now we've got the Spalding wall function in purple as well. And we can see that the Spalding wall function actually is a very good fit in the viscous sublayer and does a pretty good job in the buffer layer of capturing that observed behavior, and then overpredicts slightly in the log law region. So the Spalding wall function is one approach we could take. However, most CFD codes actually tend to use a proprietary blending between the linear and log law wall functions in that buffer layer, so it's still quite uncertain what's actually going on there and how accurate that treatment is in the buffer layer. So one thing we often find in CFD manuals is that the wall treatment is often called automatic, and what this means is that the CFD code will switch between that linear variation and that logarithmic variation depending on the local value of y+. And this is without the user having to explicitly specify what region y+ is going to be in ahead of time. Remembering, of course, that when you create the mesh initially you don't know what the value of y+ is, and actually y+ varies and changes as the simulation converges. So the CFD code on the fly will switch between the appropriate wall treatments without any user input. And this is often why wall treatment is called automatic or blended. We don't have to specify ahead of time what we're going to do, and the user can simply specify a boundary as a wall, and the CFD code will do the rest. So now we've had a bit of background, now we're actually going to dive into what the CFD codes actually do behind the scenes. And this does take a little bit of thinking about. In the diagram on the left, you can see we've got a typical cell with the height of the centroid is yp normal to the wall. Now, what we need to think about is that the velocity at the wall is 0, the no slip condition, and we actually know the velocity at the cell centroid as well, which we're going to call up here. So we know the velocity at the wall and we know the velocity in the cell centroid. So actually what we need to know is we need to know the gradient and the wall shear stress normal to the wall. And if the cell is very close to the wall in the viscous sublayer, we know that that variation is linear, and so actually it's very straightforward to calculate the wall shear stress, and we can do that using equation 7. Now, what if the variation between the cell centroid and the wall is non-linear? So what if our cell is actually in the log law region? Again, we can evaluate the expression for the wall shear stress by substituting in that logarithmic profile, and we get an equation for the wall shear stress. We can work out the gradient normal to the wall from this. So this is where we actually have to do a bit of thinking. And if we remember that we know the velocity at the wall, we also know the velocity at the cell centroid from the CFD solver, and we're trying to work out the gradient. Now, in a second order finite volume approach, we want to use the same method to calculate the gradient across the entire mesh. And using second order, so the variation is linear across the cells. Now, if we assume the variation between centroid and the wall is linear, and we're in the log law region, the wall shear stress will be predicted incorrectly. So what we want to do is correct, and to make sure that the wall shear stress is computed correctly. And the way we do that is we equate those expressions for the linear profile and the logarithmic profile for the wall shear stress, as we can see in equation 9, and rearrange, and we get an expression for the wall viscosity. Now what this is the viscosity that if we used, even though the gradient is actually non-linear, then if we use that in a linear expression, we would get the same wall shear stress. So I think we need to take a step back again and think about what we're doing here. Is that if our cell is in the log law region, we can use this wall viscosity, we can modify the wall viscosity, and then the wall shear stress we predict, assuming that the gradient is linear, will be the same as if it wasn't. And then we can use the same method of calculating the gradient across the entire mesh and get the correct solution. So this is often why in some CFD codes you may see the wall viscosity. It's a way of correcting to ensure that we get the same wall shear stress and the same gradients. Now for convenience, if you actually dig into the CFD code, what we find is that CFD codes often express the wall viscosity as the summation of a laminar and a turbulent component. And of course, if your wall adjacent cell is in the viscous-sub-layer, the wall viscosity will be entirely laminar and that turbulent component is 0. But then if we're in the log law region, the wall viscosity will be increased, and hence we can just use a simple conditional if statement to calculate our wall viscosity. So this allows our CFD code to use the same calculation of the gradient across the domain. We know what the velocity is that wall adjacent cell centroid, and all we have to do is a conditional if statement to switch between the calculation of the wall viscosity to ensure that we get the correct wall shear stress. So now, just wrapping up with some recommendations for what value of y plus should I actually be aiming for in my CFD simulations. And the first point is trying to always avoid placing cells in that buffer region, because we don't really know the accuracy of the wall treatment when the cell's in the buffer region, and so actually if we have our cells there, the solution is quite likely to be inaccurate. Now, one thing we should also remember and think about here is that that universal profile, the experimental measurements and the DNS data, were extracted from a plain parallel flow where there was no separation, no curvature, and no strong pressure gradients. So if we're in a flow scenario where separation, curvature, and strong pressure gradients are present, say unsteady flow behind a cylinder, for example, then that universal profile is no longer likely to be accurate and valid. And so if we use this wall treatment approach, then the flow solution that we predict is highly likely to be incorrect and wrong. So really what we have to do is have a think about the flow physics that we're actually trying to represent when we're choosing our y plus values. And ideally, if we can, we always want to try and get our y plus less than 5 so that we're in the viscous sublayer. Now at this point, it's worth noting that for some external aerodynamic simulations where separation and curvature effects are very strong, the conventional wisdom is to have a y plus approximately equal to 1. Now, this may appear a bit counterintuitive at first because we saw that actually the viscous sublayer extends from a y plus of 0 to a y plus of 5. But we should remember that actually the shape of that universal profile and the onset of the buffer region don't necessarily occur at y plus equal to 5 when we have strong curvature, separation, and pressure gradient effects. And so actually conventional wisdom, trial and error through the industry has shown that actually reducing the y plus down to 1 is sufficient to achieve an accurate solution, because when the y plus is 1, then the flow variation between the wall and the wall adjacent centroid is linear, even under separation, curvature, and pressure gradient effects. But that may not be very useful. One piece of advice, which is always very good, is if possible to run a 2D check or to compare your results against experimental measurements to actually see how well is my wall modelling approach actually capturing the flow physics. And just to give you a quick example of that, what we've got here is an example of a 2D aerofoil. So this can represent a slice through your 3D wing or 3D wind turbine or compressor blade, and you can use the 2D simulation to actually investigate the accuracy of the wall function and the wall resolved approaches, because we can use a much finer mesh. And what we see for this 2D aerofoil is that actually for angles of attack less than 8 degrees, the solid line, which is the wall resolved approach, and the dashed line, which is the wall function approach, actually get very good agreement. So for this aerofoil, as long as the flow is attached and at low angles of attack, actually the wall function would be very reasonable for our wind turbine blade or our wing. But as soon as the flow starts to separate, an angle of attack of 10 or 12, then actually we have to go with the wall resolved approach and try and drive that y plus down to 1. So just to wrap up with some useful references, always worth looking at the ANSYS Fluent user manual, has much excellent help and advice for you if you're actually running your CFD simulation. And I've also included the reference here for the original direct numerical simulation data that were used to derive and fit these wall functions to, and also a technical report from Chalmers University, which really goes into a lot more depth than I have here about the wall functions for velocity and also for temperature and other turbulence quantities, which I haven't covered. Of course, I'll include all references in the description down below, and if you have any comments, suggestions, or even noticed any errors, feel free to drop a message or leave a comment.